Welcome to this presentation. You are watching a Vlsi design lecture series. Today we are going to focus on pipelining and parallel architecture. Pipelining is a popular design technique often used to accelerate the operation of data paths in a digital processor. And we can understand the concept of pipelining by examining this example. The goal of this presented circuit is to compute log of A plus B, where both A and B represent streams of numbers. That is, the computation must be performed on a large set of input values. The minimal clock period T minimum necessary to ensure correct evaluation is T minimum is equal to TCQ plus TPD logic plus TSU, where TCQ and TSU are the propagation delay and setup time of the register respectively. And we assume that the registers are edge triggered registers. The term TPD logic stands for the worst case delay path through the combinational network, which consists of the adder, absolute value, and logarithmic functions. In conventional systems that don't push the edge of the technology, the later delay is generally much larger than the delay associated with the registers and dominates the circuit performance. Assume that each logic model has equal propagation delay, and we can notice that each logic model is then active for only 1/3 of the clock period. If the delay of the register is ignored, we can consider only 1/3. Okay. For example, the adder unit is active during the first third of the period and remains idle. That is, no useful computation will be done during the other 2/3 of the period. So, pipelining is a technique to improve the resource utilization and increase the functional throughput. Assume that we introduce registers between the logic blocks as shown in this second diagram. So this causes the computation for one set of input data to spread over the number of clock periods. The result for the data set of A1, B1 only appears at the output after 3 clock periods, and at that time the circuit has already performed the parts of the computation for the next data sets, that is A2, B2 and A3, B3. The computation is performed in an assembly line fashion and hence the name pipeline. The advantage of pipeline operation becomes apparent when examining the minimum clock period of the modified circuit. The combinational circuit block has been partitioned into the 3 sections, each of which has a smaller propagation delay than the original function. And this effectively reduces the value of the minimum allowable clock period, that is T minimum pipe is equal to TCQ plus maximum of TPD, add TPD, absolute and TPD, logarithmic. That is the propagation delay of adder, absolute value and logarithmic value has to be taken into account. The maximum value that should be taken into account plus TSU. So suppose that all logic block have approximately the same propagation delay and that the register overhead is small with respect to the logic delays. The pipelined network outperforms the original circuit by a factor of 3 under these assumptions, that is T minimum pipe is equal to T minimum by 3. The increased performance comes at the relatively small cost of 2 additional registers and an increased latency. So this explains why pipelining is popular in implementation of very high performance data paths. Now let us focus on latch versus register based pipelines. Pipeline circuits can be constructed by using level sensitive latches instead of edge triggered registers. Now you can consider this circuit where the pipeline system is implemented using pass transistor based positive and negative latches instead of edge triggered registers. That is, logic is introduced between the master and slave of the master slave system. So here we use a clock bar notation to denote the two-phase clock system without loss of generality. And latch based system gives significantly more flexibility in implementing a pipeline system, and they offer high performance. When clock and clock bar clocks are non-overlapping, correct pipeline operation is obtained. Input data is sampled on C1 at the negative edge of the clock and the computation of the logic block F starts. and the result of logic block F is stored on C2 on the falling edge of the clock bar, and the computation of logic block G starts. The non-overlapping of the clocks ensures correct operation. The value stored on C2 at the end of the clock low phase is the result of the passing the previous input that is stored on the falling edge of clock on C1 through the logic function F. When overlap exists between clock and clock bar, the next input is already being applied to F, and its effect might propagate to C2 before clock bar goes low, assuming that the contamination delay of F is small. In other words, a race develops between the previous input and the current one. Which value wins depends on the logic and is a function of the applied logic inputs. The latter factor makes the detection elimination of race condition non-trivial in nature. So, an improved logic style for pipeline structure is NORA CMOS. The latch-based pipeline circuit can also be implemented by using C-squared MOS latch, as you can see in this figure. And this operation is similar to C-squared MOS, and the topology has one additional important property, that is, a C-squared MOS based pipeline circuit is race-free as long as all the logic functions F that is implemented by using static logic between the latches are non-inverting. The reasoning for this argument is similar to the argument made in the construction of C-squared MOS. That is, during a 0-0 overlap between clock and clock bar, all C-squared MOS latches simply to pure pull-up networks. The only way a signal can race from stage to stage under this condition is when logic function F is inverting, where F is replaced by a single static CMOS inverter. So similar consideration are valid for the one-to-one overlap also. So based on this concept, a logic style called NORA CMOS was conceived, and it combines C-squared mod pipeline registers and NORA dynamic logic function blocks. Each model consists of a block of combinational logic that can be a mixture of static and dynamic logic followed by C-squared MOS logic. Logic and latch are clocked in such a way that both are simultaneously in either evaluation or hold mode, that is pre-charge mode. A block that is in evaluation during clock is equal to 1 is called a clock model, while the inverse is called clock bar model. Examples of both classes are shown here in this diagram, and the operation of modes can be summarized as for clock is equal to 0, clock block will be, logic block will be pre-charge, latch will be hold, and clock bar block, logic block will be in evaluate mode and latch will be in evaluate mode. For clock is equal to 1, the clock block will be in evaluate mode in both logic and latch, whereas the clock bar block are in pre-charge, logic block is in pre-charge, and latch block is in hold mode. A narrow data path consists of a chain of alternating clock and clock models. While one class of models is pre-charging with its output latch in hold mode, preserving the previous output value, the other class is evaluating. Data is passed in a pipeline fashion from model to model. NORA offers designers a wide range of design choices, and dynamic and static logic can be mixed freely, and both clock N and clock P dynamic blocks can be used in cascaded or in pipeline form. Although this style of logic avoids the extra inverter required in domino CMOS, there are many rules that must be followed to achieve reliable and race-free operation. As a result of this added complexity, the use of NORA has been limited to high-performance applications. Thank you.